Okay, today we're finishing off AVL trees, at least I hope we are, and there's still a programming assignment 2 that's out, and there are clarifications, there are clarifications and updates for, there are clarifications for PA2 on Piazza that you might want to look at. Just basically a more clear explanation of what the level number is doing in the process of determining which pixels are put into the structures and which are not. So today's plan is to do double rotations and to do remove, so that you get a picture of all the operations on AVL trees. But before we do that, we have to warm up. So this is a warm-up which is an extremely interesting warm-up. It's a question about how do you show that AVL trees are short? So we know that AVL trees are something like a constant times log n in height, no more than that, less than or equal to some constant times log n. And this is supposed to give you a feeling that you understand why that's true. In fact, it'll prove that it's true. So, hopefully. And so we start off here by saying there's this function n. So we're kind of starting off backwards. We're interested in showing that the AVL trees are short, which means we want to show that their height is small, right? But what we're going to first look at is how many nodes we can cram into an AVL tree. How many nodes are in the smallest AVL tree that has a particular height. So n of h is the fewest number of nodes you can put into a tree, into an AVL tree, and have it be of height h. Okay? Our goal is to show that AVL trees are short. So we will be talking about calculating bounds on n of h, the number of nodes in the smallest AVL tree that has height h. Do we want to show that n of h is big, or do we want to show that n of h is small? If we want to show that AVL trees are short. Hold on just a sec. It's a really good question to think about. We're going to vote. I think we'll vote. How much time do you need in order to vote? You ready to vote now? Yeah? You're all ready to vote now? Okay. How many people think that what we want to show is that n of h, we're trying to show that all AVL trees are short, meaning their height is small. What do we want to do to show that the height is small? Do we want to show that the number of nodes in the fewest node tree that has height h, do we want to show that that number is big? Do we want to show that number is small? Oh, that's interesting. So the bigs have it. Yeah, we want to show it's big. We want to show that in order to get to height h, you have to put a lot of nodes into the AVL tree. You can't get there unless you put a lot in. So, okay, that tells us something about what we're going to be wanting to prove inside of these, about this function. So the other thing to warm up with is what's the number of nodes in the smallest AVL tree that has height 0? What's n of 0? Height is 0. Okay, again, we'll vote. Is n of 0 0? Is n of 0 1? Okay, good. You're starting to make me worry there, but that's okay. N of 0 equals 1. How about n of 1? What's n of 1? That's a height 1 tree. How many nodes in the smallest AVL tree of height 1? Okay, 2, 3. Is this an AVL tree? Well, you check the balance condition. Right? The heights of the children of the root node, we don't have to worry about the leaf because its children are the same. They're both nil, so that's okay. But what's the height of the children of the root node? Well, this child has height 0, and this child is null, which means it has height -1. Do those heights differ by 1? Yeah. No, that's an AVL tree, and it only has 2 nodes. So, and its height is 1. So this is 2. Certainly it can't be 1, because if it was only 1, then there wouldn't be enough to make height. Anyway, so it's 2. What is n of h? That's what this picture is about. What do you know about the children of the root of an AVL tree, that's the smallest AVL tree that has height h? What do you know about those children? Smallest AVL tree of height h has 2 children. What are the children's heights? Yeah.
Would it be the height are h-1 and h-2?
Okay, the height has to be, just a second, we have to pause and wait a second. Why are they height h of -1 and h -2? Why is my AVL tree, my smallest AVL tree of height h, why does it have children of height h -1 and h -2? Well, okay, I'll ask it in separate pieces. Why does it have a child of height h -1? Because it has height h, and the height of a tree is the maximum height of the 2 children plus 1. So if one of those children doesn't have height h -1, if it has height smaller than h -1, then the tree doesn't have height h. So we know that one of the children has to have height h -1. That's great. Why is one of them of height h -2? Yeah.
Because if they were both height h -1, then it wouldn't be the smallest AVL tree, and if it was less than h -2, then it would be AVL.
Yeah. If we made it h -1, if it was height h -1, then that would be wasteful. Because the only property that we need is to preserve the AVL tree property, which says that the height of the 2 children have to be within 1 of each other. So we know that one of them has to be height h -1, but that means the other one could be of height h -2 and still obey the AVL property, and decreasing the height of the tree decreases the number of nodes in it. So one of them should be of height h -2, one of them should be of height h -1, and what should they be? That's trees, but what kind of trees should they be? Yeah, they should be binary. They should be binary search trees. Yeah, one more step, 2 more steps. They should be AVL trees, and they should be one more. What kind of AVL tree? The smallest AVL tree of height h -1. So this guy is the smallest. So how many nodes is in this guy? How many nodes are in this guy with h -1? Yeah, you guys got recurrence relations down. That's the n of h -1 tree. This guy, that's the n of h -2 tree. So what am I going to write here? This n of h is equal to what? The number of nodes in the tree of height, smallest AVL tree of height h is equal to, well, there's the root. Then there's the nodes in the left subtree. Then there are the nodes in the right subtree. And that's it. So now we have a great recurrence relation to tell us exactly what the number of nodes in an AVL tree of height h, the smallest AVL tree of height h, contains. But this looks complicated. Yeah?
Oh, just to confirm. Also, the reason of one of the subtree has height h minus 1 is that way we can check in height tree has height h, right?
Yeah, you need somebody to have height at least h minus 1. And they can't be height more than h, because then there would be h or more. That's crazy. And it can't be of height less than h minus 1, because then the whole tree would be shorter than height h. So we know one of them has to be h minus 1. And the other one has to be within 1 of that height. All right, so now the distressing part is that this is complicated. But we don't care, because all we care is to show that n of h is big. Right? We want to show n of h is large. So here's the trick. All we want to do is show that n of h is large. Let's just go in there and say this is greater than what? What is this greater than that would still sort of give you the same feeling, but not be so precise? 1 plus n of h minus 1 plus n of h minus 2. It's a complicated recurrence relation. We're saving that for the homework. For the talk here, all we need is an approximation to actually tell you or show you that the height is small. So what kind of an approximation do you think you want to use? Yeah. Okay, we could do that. This is certainly bigger than n of h minus 1 plus n of h minus 2. That's definitely true. I want even simpler. Yep.
2 times n of h minus 2.
This is also bigger than, whoops, that's a weird thing. It's also bigger than, 2 times n of h minus 2, because n of h minus 1 is certainly bigger than n of h minus 2. So this n of h minus 1 plus n of h minus 2 is bigger than 2 times n of h minus 2. That's pretty simple. You know how to solve these things? Yes. Did it on the midterm multiple times. What's the solution to this recurrence relation? What's basically happening? I'm multiplying this value by 2 and I'm decreasing the argument by 2. So it's going down by 2, 2, 2, 2. How many times does it go down until I get to something like a base case? How many times do I repeatedly do substitution until I get down to the base case? I'm subtracting 2 each time? No? You're paralyzed. Don't be fearful of this. Is one of the nicest recurrence relations you're ever going to see, right? It's just n of h equals 2 times n of h minus 2. If that was n of h minus 1 instead of n of h minus 2, then you would be home free, right? You're worried about the h minus 2, right? Or not? Or are you just sitting there waiting for me to solve this? That's not good. What is this going to be? What's the solution to this? N of h is something like, okay, when in doubt, if you really don't know, what's n of 2? N of 2 is greater than 2 times n of 0. N of 2 is greater than 2. What's n of 3? N of 3 is greater than 2 times n of 1, 4. What's n of 4? N of 4 is greater than 2 times n of 2, 4. What is in a 5? Gee, it's going 1, it's going 2, 2, it's going 4, 4. What do you think this is going to be? 8, 8, 16, 16, 32, 32. What's the answer going to be? N of h is some power of 2. No, not equal. Bigger. Bigger than some power of 2 yeah, h over 2. In fact, it's the maybe the ceiling of h over 2. Okay, so if n of h is greater than 2, so the ceiling of h over 2, how does that help us show that the height, that AVL trees are short? Well, if I take log of both sides, you know what? If it's greater than 2 to the ceiling of h over 2, then it's also bigger than 2 to the regular old h over 2. So let's just do that. Anybody feeling a little nauseous? Like a little bit like approximations are not fun? Like we're throwing stuff away. What are we doing here? Like it's stupid. We could get a better bound if we kept all this stuff. Why am I doing this stupid stuff? Because it doesn't affect the asymptotics of the answer. So you have to sort of do this to the point where you understand that. But that's what's going to happen here. If I look at this and I want to get a relationship between height and number of nodes, I want to get a relationship that says, you know, if I have a tree that has n nodes in it, then it has height something. I have to get an inequality that involves height and number of nodes. I have an inequality that involves height and number of nodes. I just have to simplify it. So this, if I take log of both sides, I get that log n of h is bigger than h over 2. And if I, monkey around with that, I get h is less than 2 times log n of h. This looks good. This is relating the height to the number of nodes n, and it's saying that the height of the tree that has the fewest number of nodes, the smallest AVL tree with height h, the smallest AVL tree with height h has height h that's smaller than 2 times log the number of nodes. So every AVL tree is going to have a number of nodes. If it has height h, it's going to have a number of nodes which is more than that. So this is going to be less than or equal to 2 times log n for AVL tree with n nodes and height h. Because n of h is the smallest AVL tree, and it's the number of nodes in the smallest AVL tree of height h. So any AVL tree with n nodes that has height h has to obey h is smaller than 2 times log n. Is this okay? I mean, what this is, it's kind of the first time that we've been a little bit loose with bounds, and we've done approximations, and we've thrown things away. We've basically said, Here's a big approximation. Versus 1 plus n of h minus 1 plus n of h minus 2. That's a pretty big approximation. But at the end of the day, and even this was an approximation, upper bound, even that, it didn't matter, because at the end of the day, when we figure out what's the relationship between the number of nodes and the height, it's still that the height is less than log n, some constant times log n. Yep.
How did you get the inequality 2 times log of the number of nodes for a tree of height h is less than 2 times log n?
Well, n, I'm assuming here that n is an AVL tree. N is the number of nodes in an AVL tree of height h. That's what this statement at the bottom says. So if I have any AVL tree with n nodes and height h, then the number of nodes that it has, because it's a tree of height h, that number of nodes has to be bigger than n of h.
Or what about the next part where you say that value is less than 2 log n?
That's what I just said, this part right here. This,
What's the difference between capital N bracket h and just little n?
little n is the number of nodes in an arbitrary AVL tree of height h.
Oh,
Any tree that has n nodes and height h is, I can make this statement about it.
and so like the nh is referring to the number of nodes in the smallest AVL tree.
Correct.
Oh, okay.
That's what, exactly. N of h is this number of nodes in the smallest AVL tree of height h. Yeah.
So how does this show that like n of h is big?
N of h is bigger than 2 to the h over 2. Our recurrence relation was just about n of h. And all we showed was that n of h is bigger than 2 to the h over 2.
How does showing like n of h is big show that the h is short?
Did you not believe the math?
No, so I get the math, but like
Oh, okay. Then everything's good. No.
like
Math
like
is-
intuition.
Oh, the intuition. So what we showed was that if I want to look at the smallest AVL tree of height h, that AVL tree has to have a lot of nodes in it. That means that any AVL tree of height h has to have a lot of nodes in it. So this is saying a lot of nodes is 2 to the height, 2 to the parameter h. And that's where we get the relationship between height and number of nodes.
So like a lot of what do you mean by like a lot of
I mean like 2 to the h over 2.
okay, because like if there was like barely any nodes, then it probably wouldn't be able to.
Right, if it was not enough nodes, either it wouldn't have height h or it wouldn't be an AVL tree.
It wouldn't be like that.
Right. We found the size of the smallest AVL tree of height h, and that's a good thing to know. The size of the smallest AVL tree of height h is like something that's saying, well, when we find out that the number of nodes in that is big, then we know that the number of nodes in any AVL tree of height h is going to be big, and that's what we use down here to say if you mean any AVL tree of height h, I get a lot of nodes.
So big or small in this context is like referring to like any arbitrary binary tree. Well, even one side would be like evaluation.
No, this is only referring to this function n of h.
Yeah, but like by big, bigger than or having more nodes.
Oh, I see. No, what I mean by big here is, do I want to show a greater than or equal to, or do I want to show less than or equal to? Like when we talk about running times and we have a recurrence relation and you want to show that the algorithm works quickly, then the recurrence relation, you want to show that the running time is less than or equal to something, right? In this case, we want to show that n of h is not small. We don't want to show that n of h is less than or equal to something. We want to show that n of h is bigger than something. We want to show that the number of nodes in the smallest AVL tree is big because we want to show that no matter what happens, you need to cram a lot of nodes into an AVL tree to get it to go to height h. And if you do that, then I get a relationship between height h and the number of nodes in the tree. It's got to be that h is less than some function. In this case, it's 2 times log n. This is not, I'm not, anyway, this is not easy. This is a little bit complicated, it's a little bit twisted, and it's also got a little bit of approximation in there that should make you feel a little uneasy. Because how did I know that this was going to work out this way? I'll tell you, I didn't. I had to work it out. I had to know that the approximations were going to work. But I had a feeling that they would be okay as I went along, because I knew that at the end I'd be taking a log, and logs forgive you. Very forgiving. Yep.
Oh, so the fact that we got h is less than 2 of log n of h shows that the density of the tree is quite high, because like we have to, because the height is the log of the number of nodes, so the number of nodes have to be fairly high for us to reach h.
That's correct.
Yeah.
Okay. Everybody reasonably okay? All right, so now we're back to talking about operations on AVL trees. This is the last thing that we looked at before. It was a double rotation. Remember, rotations are this thing where you basically rotate either to the left or the right to bring a tree into balance. So in this particular example, we use rotations not to bring a tree into balance at first, but to set it up so that when we do the other rotation, we get it into balance. So the first rotation is the pink rotation, and it sets us up by putting 5 at the top, with a one child of 7 who has 2 children. This was after we inserted 6. This is after insert 6. So we have this new leaf 6, which was causing our tree to go out of balance. In fact, the unbalance happened right here at the node numbered 4. And because we needed to balance, because it wasn't one of these simple just a left rotation will work, we needed to do a double rotation. And so now here we have a 2-step double rotation. The first comes the rotate right, and then comes a rotate left. And after that, we get we restore the balance of the tree, and in fact, we decrease the height of all of these nodes. These nodes. They used to be 3 and 4, and they drop down to 2 and 3 again. Okay, that's the double rotate. It looks like 2 single rotates applied in succession. Here's the incredibly clarifying picture, which has all of the heights indicated in it. For this picture, it's working for the same rotation we just looked before, rotate right-left. Rotate right-left occurs when you find you've inserted something, and the insertion could have occurred here, or it could have occurred here. Doesn't matter. What happens is that insertion causes the height of B to increase, which causes the height of C to increase, which causes C to become out of balance with its sibling. So it has height h plus 1 versus height h minus 1. And now we have to fix that. And the way you can think about doing this is either by doing... Oh, sorry. Go.
So, did you say that it causes the height of B to increase when you do the insertion?
Yeah.
So are X and Y both the same height after the insertion?
No. No, the insertion will only occur in one of X and Y. And that insertion causes one of X or Y to increase in height. And they go up to one of them is height h minus 1, but previously they were of height h minus 2. And we know that because if they were of height h minus 1, which they are now, then this would have been out of balance. It would have been an out of balance AVL tree beforehand. So we know that one of these two trees, either X or Y, had to have increased, and it had to become the new tallest child of the node B. Okay, and if you like to think of this as a double rotation, you can think of it as this kind of a picture, 2 single rotations. Or if you like to think about pointer manipulation, you can just say, you have to change this tree, this one with the sort of A, C, B elbow, into this tree where A is no longer the root, but B splits A and C, and then the subtrees hang off in binary search tree order. Remember, if you get confused, whatever you produce after a rotation still has to be a binary search tree. It has to obey the search tree properties. So the numbers in the left subtree, the keys in the left subtree have to be smaller than the roots key, and the ones in the right subtree have to be larger than the roots subtree. Okay, and so now when that happens, when we perform this rotation, we squish everything up again to be shallow, and the height decreases by 1 at the root. In other words, it goes back to being the height it was before we performed the insertion. Yeah.
So for this diagram, so when we were performing the final right rotation, because B has a non-null left child, so we will move that child to become the new right child of A, right?
The last rotation that's performed here is a left rotation.
Oh, sorry, left rotation.
Okay.
Also, we'll move the left child of the node that we're moving up to become the new right child of the node that we're shifting down.
Yeah, maybe it'd be worthwhile looking at this. So you're talking about this step here.
Yeah.
Yep.
Also, I'm guessing if 5 had a left child, it would become that child would be moved to the right. Would become the right child of node 4, right?
All follows the binary property, binary search tree. Okay? Ready for some code? Yay! No. Oh well, too bad. There's some code. So this is the insert algorithm. The insert algorithm, first of all, it acts just like insertion in a binary search tree. It finds the location for the new key, which is some leaf location, and it adds the key to the tree as a leaf. So the new key becomes a leaf. Then what happens when you come up the tree, either by coming out of the recursion or by following parent pointers, depending on what you want to do, as you go up the tree from the new leaf, you search for imbalance. And you also update the heights of the tree, of the nodes that you're encountering. Because when you add a new leaf, it's possible that by adding that new leaf, you've increased the height of the parent node, which might increase the height of the grandparent, which might increase the height of the great-grandparent, which might, et cetera, as you go up. So you do that update as you go up, and every time you're doing that update, you're checking to see whether the balance criteria is satisfied or not satisfied, because the heights have changed potentially. And then eventually, if the heights don't change, you don't have to worry anymore. But it could be that you run into a situation which is shown here. This is where you run into an unbalanced ancestor of the leaf node that you've inserted, which is shown in black. So this node right there, that's supposed to represent the unbalanced ancestor that you've reached. And it is, depending on its relationship to the place where the insertion occurred. So the insertion occurred in this little triangle down here. So this represents the insertion occurred here. So the little triangle is where the insertion was, and if the insertion occurred in that subtree and you see an imbalance that's occurred coming back up, that's the left child, that the insertion occurred in the left child of the imbalance node, then you perform a single rotation, a rotate right. If, on the other hand, it was a case where the insertion occurred in the right child of the right child, then you do a rotate left. Otherwise, you're in one of these elbows, these zigzag things, and you perform a double rotation. Double, either you rotate left and then right, in this case, or you rotate right and then left, in this case. All depending on where it's coming from. Yep.
So maybe you could quickly demo the LR case.
Yeah. We'll see it in just a brief second. Everybody good with the scheme for doing insertion? Because we're going to do an example. In fact, we're going to do 2 examples. No, in fact, we're going to do 3 examples, but they're going to be quick. So let's do insertion into this AVL tree. First of all, are you sure that this is an AVL tree? It's very likely that I could have made a mistake. I am not perfect. Everybody happy? Is this an AVL tree? Okay. I think it's an AVL tree too. But who knows? Now I'm going to insert 3. So I come along with 3 and I compare it to 10 and it says smaller. So it goes down here to 5 and I compare 3 with 5 and it says smaller. And I go down to 2 and I say 3 compared with 2 is bigger. So I stick 3 on the bottom here. And now I follow the rule of assigning it a height of 0 and then going back up to update the heights of the nodes and check for imbalance. So the parent node now is no longer of height 0, it's of height 1, which is the max of the heights of the 2 children plus 1. And now I check this balance. Is this node out of balance? Well, one of its children is not there. That means it's got a -1 height. And the other one has height 0, so we're still okay. Now I go up to 5. 5 now has height, well, 1 plus the max of 1 and 0 is 2. Is 5 out of balance? I check. This is a 1. This is a 0. Everything's okay. Okay. Now I have to go back up to the top. Now this is the height of the root is 1 plus the max of the 2 heights here, although height of the root doesn't change. So I'm done, and there was nothing. This is the no imbalance case. That's simple insertion. So now we have this tree, and now into that tree we insert 33. We compare 33 to 10, it's bigger. 33 to 15, it's bigger. 33 to 20, it's bigger. 33 to 30, it's bigger. We go up from below, starting with the 0. We update the height of the parent to 1. We check balance condition. Happy? Happy? Okay. Then we go up another level. Now we take the max of the 2 children's heights plus 1. That becomes a 2. Happy? Well, we're happy at this node, but we're not going to be happy at the parent node, because now the height of this node is 2 and the height of that node is 0. So the 12 and the 20, those 2 nodes are children, they're siblings, and they're off by more than 1. So we know that this is a problem. There's an imbalance that occurs here. What operation are we going to use to fix this imbalance? Don't look at the top. What are we going to do to fix the imbalance? Oh, it shows us the case. You don't know what to do. What do? Rotate left. So it's a single rotation, because this path that we followed from where we inserted, this path is a path that's the first 2 steps of that path go to the right. So that determines which rotation we'll use. So rotate left. So we take our imbalanced tree and we perform this rotation to reassign the children of the subtree that's currently rooted at 15, to reassign those subchildren so that the subtree becomes more balanced. It's restored to its balanced condition, and we do that basically by pointer manipulation. We reassign a bunch of pointers so that we get this new tree. And now in the new tree, the actual height, the old height of, whoops, I shouldn't scribble that out. The old height of 3, the one that we just calculated, and it's the parent of it's the root that's out of balance. It restores back to its former value of 2, and so we don't have to do anything else to update this tree. No more rotations.
So to figure out which case we're in, we're looking at the first 2 edges from the balance.
Correct. That's right. That's what those little pictures mean. It's like these little pictures are just talking about the first 2 edges coming down from the imbalance node.
Yeah, not from one of the insertions. It could be more than 2.
Right, that's why this is like a little triangle. It's supposed to represent the fact that that insertion occurred in that subtree.
Somewhere in that.
That's right.
Okay.
Maybe I'll write that here. Insertion occurred here, blah, in this subtree. It all depends on the first 2 edges coming down from the node that's out of balance. Okay, rotate left. We did the rotate left. Here's the code for rotate left. It's pretty much what you expect. It's taking a reference parameter, A, which is pointing to the root where the imbalance occurred, and it is restructuring by doing 3 pointer changes. Let's find them. It has to change this, it has to change this, and it has to change this to change from this tree to that tree. There are 3 pointers that need to change. This is called A. This is called, no, let's not use A. This is called 1. This is called 2. And this is called 3. And now here's the game we're going to play. You have to tell me which line of code changes which pointer. It's going to be fun. What line of code changes pointer number 1? The A is a reference parameter, and assigning it to B changes it to be the pointing to the node B. Okay? What is the line that changes pointer number 2? Not too quick. We have to think about this. I have to think about this. What's being changed is the right pointer of A. So the right pointer of A is getting updated someplace in here. It's going to point to, instead of pointing to B, it's going to point to the left child of B. So presumably there's some code in there that says that, and yeah, you're right, it's right there. A right equals B left. Good. And where's the third update? It's the only other assignment here. The only other assignment that really is happening is that. The other one here is just a declaration so that we can find the node B. We can get the address. So those are the 3 pointer manipulations that happen here. The alterations in the structure. Now in between, before we return, we update heights of A and B because those heights might have changed. A, for example, no longer has B as a child. A is now the child of B, and so its height would have changed. And B's height would have changed as well. This is it, yeah.
Oh, sorry, I'm still not too sure about like how you change the A pointer, where you just put like A equals B.
Oh, okay. Are you unsure because B is not a reference parameter, or are you unsure because A is a reference parameter, or?
Like, normally wouldn't that mean like node A is now node B?
What it means in this context is that because A is a reference parameter, it means whoever called this function to update this tree passed in a pointer, and that pointer is now going to have the value. The pointer that they passed in is going to be changed to be the pointer to the node B. So whoever had that pointer is now pointing to a new subtree. I mean, a new root of a subtree. Okay, good? Right, left.
Can I ask a question?
Yes.
Can you say A equals B before updating heights?
Yes.
So, like A equals B, never change the heights of A. Everything like that.
Well, the only thing that's happening here is that you're just changing the name of the pointer. So what it points to has a field in it that's called height, which update height is changing that field in the node. So it's going to be the correct height, but its name now changes from being pointed to by A to being pointed to, well, instead of being pointed to by B, it's now pointed to by A. B actually just goes away, it's a local variable. Okay, okay, we got 2 minutes to do this. It'll be great. Insert 18. We know how to do this. Zoom, 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 zoom. 18. Update heights. 0, 1, no imbalance yet. 2, uh-oh, we're running into trouble again at 15. Problem. Children at 15 are out of balance. One has height 0, the other one has height 2. So we're off by more than 1. This case, we have a zigzag path that goes first to the right and then to the left. So we are in the case rotate right left. And this is the picture that we want to implement, where we bring first 17 up by performing the rotate right, and then we perform the rotate left. On the blue nodes, they bring the tree back into balance. That's what we want to implement. We have 1 minute to describe the implementation. Do you think we can do this? It's 2 lines of code. Wow. Isn't that great? Because you basically just do rotate right on the right child of A, and then you rotate left at A. Isn't that cool? This is the best part of the lecture, really, for me. Makes me very happy. Let me tell you one more thing. Deletion. If you remove from a tree, an AVL tree, if you try to remove, for example, node 1 from this AVL tree, you are going to perform several rotations. So you can't stop. It still takes order log n time, but it involves multiple rotations. Possibly a rotation at every level of the tree, but only one at every level of the tree. Okay, I will see you on Monday. We'll talk about hashing.